안녕하십니까. 유엔미래 포럼의 박영숙입니다. 박영숙의 미래TV 오늘은 하이퍼사이클이 무엇인가. 이 투피 살리바 선생님은 IEE의 AI 표준 위원장입니다. 글로벌 AI 표준 위원장. IEE는 여러분들이 아시죠. 굉장히 오래된 단체이고 모든 분야에서 표준을 만들고 있고요. 이분은 어제 우리가 국회에서 국회 도서관에서 AI 소울 포럼을 했어요. AI 소울 포럼의 기조연설자로 왔고요. 이분이 하이퍼사이클을 만들어서 우리가 쓰고 있는 이 기본적인 인터넷을 AI 인터넷으로 만들겠다 이렇게 해서 개발자입니다. 이분은. 그래서 개발을 했어요. 보여드릴게요.
All again, and I feel like there's a lot of progress that happened over the years. During COVID, I ended up focusing more some of the aspects of Toda IP. I am the author of Toda IP, so of course some of the things that I do give back to society include the IEEE, like you mentioned, and before that the ACM. But my main role has been focused around the Toda IP because I authored Toda IP, and I co-authored the Toda paradigm shift. Toda paradigm shift is the maximum decentralization, effectively. So if anybody gets to more decentralization than the method that we have allocated, we're calling it Toda paradigm shift. Effectively, it's more like a paradigm shift to have every single node to be equal to another in decentralization. And this isn't about democracy, this is about security. So the more you have devices that they run the system, the more it is secure.
오케이. 이분은 한평생 시큐리티를 했어요. 그래서 그 모든 시스템의 모든 디바이스나 이런 네트워크에 버그가 가거나 뭐 아니면 바이러스가 오는 거를 막는 이런 역할을 해서 그거를 토다 IP, 토다 시스템, 토다 네트워크 이렇게 만들어 가지고 파라다임 시프트를 하기를 시도를 했고요. 그게 이제 탈중앙화를 했을 때에 여러 시스템에 문제가 생길 수가 있거든요. 그런 것을 처리하는 이런 개발자 고 블록체인을 처음 만든 분입니다. 블록체인을 아이디어를 만들고 블록체인 뭐 이렇게 해서 하고 지금은 IEEE라고 거기에 여러 위원장이 있는데 이 사람은 글로벌 AI 표준 위원장, AI의 표준을 만들기 위해서 한국에 왔습니다. 오케이.
Okay,
So,
I'm trying to put the white paper here just so then again get a very good reflection.
Right. Okay, that is.
Perfect. All right.
네.
Cool. So yes, as I've said, I've authored Toda IP, and with Toda IP, I ended up getting involved in a lot of cool projects, and one of them is called Earth-64 data structure. And with that, there's certain components called SATO server, which is it's almost in a way it's like a subset of Toda IP, but it's independent. It doesn't really need to use the protocol as Toda IP. The data structure could use any method for communication. The data structure is analogous or very similar to how we envision the IP. You know, Internet Protocol for every single machine has its own IP. With Earth-64. It gives a certain identity for every single component in less than 64 kilobyte file. And that file, it's capable of having that thing to be more like a containerized. And if it is containerized, then you can put anything of value into it. What are things of value in the world that we live in? Some of them, they are tangible things. Some of them, they are soft things. If you were to have your work done and then you want to get paid, that becomes the thing of value. You need to transmit it. But if the computer is doing a work computation, whether it is AI computation or not, after it finishes that computation, it consumes certain resources. So not only the energy, it also consumes certain intelligence, such as the program. Like if somebody wrote a program or someone else wrote AI or algorithm or whatnot, that is a thing of value that consumed time and energy using computer, all of those resources, it becomes a thing of value. That thing of value, how can you transmit it? In the world that we live in today, there's only two ways of actually transmitting this value. And those two ways in this soft value, those two ways, they depend on a third party. That third party, it's either called a bank, such as, usually refer to it as centralized, whether it is a registry. If you're transferring like the ownership of a car or something like that, you depend on that third party. And the other method is called decentralized, still a ledger. It's still a third party. So when two components are talking to each other, they need to transmit value. Although themselves they might be decentralized, but it doesn't matter. Between the two peers, it's still a third party. We don't like third parties.
위에서 아까
So-
이분이죠. 토다 IP 뭐 그다음에 데이터 스트럭처도 다시 만들었고 그다음에 Earth 64라는 것을 또 새로 만들었고 그리고 지금 우리는 이런 것들을 다 활용하면은 전부 에너지를 쓰고 그죠? 컴퓨테이션을 합니다. 컴퓨테이션을 할 때 에너지 쓰는 거, 그다음에 정보를 얼마나 갖다 주는지 인텔리전스를 쓰는 거, 그게 타임 앤드 에너지 이런 게 다 필요하죠. 그게 옛날에는 우리가 은행을 썼어요. 뱅크 해가지고 은행이 밸류 가치를 정했는데 이제 이 사람이 정하는 세상, 이 사람이 이야기하고 있는 토다 토큰 이런 거는 레저, 그죠? 블록체인의 레저. 이 사람은 또 레저 없는 걸 나중에 디센트럴라이즈드 하면은 탈중화하면은 은행 역할을 레저가 하는데 이 레저 이런 것이 나중에 밸류가 된다 이런 거예요.
그러면 어디다 기록을 해요?
응? Where do you
How to write the record? How to write blockchain record?
without ledgerless?
Yes. So that's a very good question. So first we need to ask ourselves, what is a blockchain? And many people, they say the blockchain is, they start by saying it's a ledger, which is false. A blockchain could use a ledger, but it doesn't have to be a ledger. I've said anecdotally saying like, my mom can use a vacuum cleaner. That does not mean my mom is a vacuum cleaner. So it's like she could use this something. So the blockchain could use a ledger doesn't mean that the blockchain is a ledger.
이게 사람들이 제일 잘 이해 못해요. 이 사람은 레저 리스트를 주장을 하는데 뭐 블록체인은 레저가 있어서 블록체인이라고 하잖아요. 근데 이제 레저 없이도 디센트럴하게 하고 이 사람이 뭐 걷어내고 뭐 여러 가지를 하는데 지금 이 사람이 설명하는 거는 우리 어머니가 그죠? 청소기를 쓴다고 우리 어머니 자체가 청소기는 아니다. 그래서 이제 없앨 수 있다. 베큐um 클리너를 레저 중간에 기록하는 걸 없앨 수가 있다. 새로운 아이디어예요. 그러니까 처음에 사람들이 정신 나갔다 그랬거든. 그래 이걸 만들어내니까.
이게 이해가 안 돼.
응, 만들어내니까 일단은
so
만들어서 이게 오퍼레이션 하니까.
If you were to say what is a blockchain, in a block of time, happens to be, as far as we know, to all of us Homo sapien, it happens for all of us the same way. In that block of time, there could be a lot of events that they happen. Could be one airplane is taking off, somebody's taking a picture, a person writing code. All of those events, they happen in that block of time. So if you want to take certain proofs that those those events that they happen, imagine there's a way of actually having them to be coupled, many of them, having certain one-way computations such as like hash function, each and every one of those events, you take picture of them or whatnot, and in that block of time when those events they happen, you chain them with a subsequent block of time. So you have one block of time, 1 second, 30 seconds, whatever that is, another block of time, that is a block and it's chained. In that, if you could use a ledger, that's okay. But if you depend on ledger, which is existing blockchains out there, you depend on ledger, then it's a problem. Because then it is a third party. That means that every time you need to move anything, you depend on the ledger. So The moment you depend on a ledger, then you have to take care of like the ledger. You have to start thinking about like consensus. You have to start thinking of how is it decentralized, and what's the governance, and all of the stuff. And it's like a never-ending thing. But imagine, just imagine, those events are able to be chained, and there's no dependency on ledger. Imagine. That would be cool. Now we don't have to solve someone else's problem, a ledger. Or maybe we use the ledger, maybe not, but if they are chained properly, great. Okay. Now we need to prove how this imagination actually works, and there's a lot of papers so far on Toda IP, and that's taken care of with Toda IP. What I will talk about here is that how we utilize the actual Toda IP in the actual HyperCycle. So we call that. Right.
이해하겠어요? 좀 설명해봐. 나도 잘 몰라. 이 전문가가 블록체인 전문가가 알아야지. 아무튼
토다 이해를 잘 못해가지고.
토다 IP에서 이게 해결이 돼서 돌아가요. 그러니까 토다 IP 설명을 하는 걸 들어봅시다.
It's a network communication protocol.
Yeah. Okay.
Toda IP is capable of taking a value which we refer to as Toda packet because it is the size of the network, the TCP packet, because it goes inside the TCP packet. It doesn't go on top. So every single blockchain that is out there today sits on top of this thing that's called TCP/IP. The entire internet sits on top of this thing that's called TCP/IP.
What is it?
TCP/IP. Everything sits on top of TCP/IP. That's a fact.
Okay.
When I say everything, probably 99.99% of things. Toda IP goes inside the TCP packet, not. So if you were to take the packet, and as you're sending it, the packet itself has all the cryptographic proofs of who owns that packet. And it cannot be owned by any more than one single signing device, basically one public key.
Okay,
It cannot be owned.
Sorry, but are you using for IPv4 or IPv6 or another one?
You could use whatever you want. This is TCP/IP. What TCP/IP that you're using, Toda IP is actually going inside the TCP. It doesn't really care about what the IP use.
Okay.
In fact, if you live in a country that the government forbids you from using TCP/IP or blocks TCP/IP, you could shift to Toda IP, which doesn't really rely on a TCP or an IP. It goes directly on the actual backbone of the internet. So it has the capability to do that. We haven't seen any implementation going that way. From protocol perspective, it doesn't really care about the IPv4 or IPv6. So that Toda IP goes inside the packet. Why is that so important? Is because we need to make sure that the maximum amount of speed happens between one device to the next. The entire internet, anything on the internet, the network cannot travel faster than the speed of light. Everything, that's the laws of physics. So, but it tries to get as fast as possible to get close to the speed of light. With those network packets, that's what's traveling. So if you have a value inside the network packet, and that value can be won, can be US dollars, can be Bitcoin, can be Ethereum, can be whatever you want it to be. If you're transmitting it, it has characteristics in the data structure itself that in any block of time it has only one owner. Okay? Without having to depend on a ledger. If you have this file, you have a cryptographic proof that you are the only owner of this file. The moment you take this file and send it to someone else has the proof and you lost the proof of being owner of this thing. But you had the history that you've had the owner of that. Now all this information is inside this file, but there is one thing that is global. And it has to be one thing that is global. If anybody tells you that they're able to transmit peer-to-peer without having one thing that is global, they would be either delusional or don't know what they're talking about. Like it's like you have to have something that is global, because if you don't have one thing that is global, somebody could be doing transaction in Australia, another one could be doing the exact same thing, take a copy of that and do it in Arizona, and that's called double spend. It doesn't work. So this thing that is global, is it a ledger that is replicated across the globe? Nope, it's not. It's actually only 32 characters. That's it. There's only 32 characters every 5 seconds or every 15 seconds, doesn't matter how whatever block of time that you want. That's the only thing that is replicated on every single device. The beauty of this is that there is every device that you have, you find in the internet today, in the world today. If you were to append every 30 seconds or every 15 seconds 32 characters, in the lifetime of a human, all of those combined would be equal to one single picture in data. So it's not going to be that much. So it's not, I'm not asking the devices to do something. What? They're going to keep appending that every time? They can do it, no problem. So why is that so important? Well, if the guy in Arizona receives a certain payment, and then the guy in Australia is trying to actually want to send this payment, if every device has those 32 characters, what contributed to the creation of those 32 characters is pretty much everything that happened in that block of time. They happen to each in a fully decentralized setting and using distributed computing. So there is not one computer doing the work. They end up traversing a data structure that is static. Why is that static? Because it has to, if you're doing distributed computing in a decentralized setting and there is no central company to check with, they need to traverse that and they get to the same Merkle root.
So it sounds like it gets fingerprint from every devices.
What's that?
Get fingerprint from every device.
Yes.
But
Thank you.
Anyone can hijack that device fingerprint.
Yeah, you can do whatever you want to the device, but you're not going to be able to take anything. If you take anything from the device, and let's say you take the private key, you took everything that you own by that device only, but you cannot take anything outside of to the world. So if you do steal one device, okay, it's like you stole somebody's wallet, somebody, right?
Yeah,
But you never ever take one and impact another. It's like each and every one is independent. They own what they own.
yeah, I'm not a blockchain expert, but as far as I know, so still the blockchain system is a real problem with that kind of system. So,
Is what?
So the blockchain system, current blockchain system, has some kind of copying or hallucination issue with that. I just heard, I don't know yet.
They have copy with what?
I don't know it fully, but I heard that somebody can imitate others' blockchain wallet. The problem is reported sometimes. So
What do you mean they can copy?
if somebody knows other blockchain wallets security code, then he or she can copy the blockchain wallet into if I know someone else's blockchain wallet's code, I can copy it into my device.
If you can copy someone's private key, you can steal their money. That's a known fact. We already know that. So if you can get to the private key for somebody, you steal their money.
So you mean the total IP has solved that problem?
That is not a problem. That is by construct a feature. If somebody has a private key, you have your own coin. If you lose your private key, you lose your own coin. And that is not for total IP to solve. That is that cryptographic signature 101. You can study that in cryptography school, and then when you realize that nobody is ever able to circumvent that yet, elliptic curve, for example, nobody's ever able to break that. But then you realize that it's the strongest cryptography that exists on the planet today. And if that's the strongest cryptography, we're using it for every single device, then that is as safe as anything that exists in the world today. So that's but having said that, there's a lot of people that they claim to be expert in the actual blockchain space because they just like copy Bitcoin. and because they copy Bitcoin, make some changes, and they call it like whatever smart contract, and they suddenly decide that they know how certain things should work, and then they start creating certain problems that they don't necessarily exist. They call it trilemma, for example. There is no such thing as trilemma. It's actually a quadlemma, the problem that we must be solved. And if somebody solves a trilemma without solving the quadlemma, they're missing on the point. There's still going to be some centralized points, or there's going to be something that is false. But anyway, point is that we're not here to solve elliptic curve. That works everywhere across the globe. So if you see somebody's device, you see their money.
What do you think about HyperCycle is meaning public blockchain or private blockchain?
In cryptography, if anything that is actually private, it's BS. If anybody tells you otherwise, they probably don't know what they're talking about. Because if you want to do private, you might as well just like do a private databases. There is no such thing as like private blockchain that is useful. Like you can literally do private.
HyperCycle is a private blockchain?
No. So
Public?
that's what I'm saying. It's like if anybody tells you they're doing anything that is private blockchain, it's bullshit. If the reason for why it's bullshit is because if you do private blockchain, you could do it on phenomenal databases that are very efficient. So if it's not public, then it's should not even be considered to be a blockchain. It's like just do a database, you'll be fine.
그렇게 주장하더라고. 프라이빗 블록체인은 블록체인이 아니다. 그거 하는 놈들은 좀 미쳤다. 이렇게 얘기해.
퍼블릭 블록체인이다?
그렇죠. 퍼블릭인데 뭐. 예.
Maybe some people they want to do business and then they call it private blockchain. That's okay. I mean, people they want to survive. Not here to criticize them, but it's still bullshit. Like let's call the bullshit bullshit. You know, it's like.
프라이빗은 없대. 블록체인 안에.
So.
이 사람들이 괜찮은 거는 마지막에는
If you want to have a call or talk about to the IP, happy to talk about that. I mean, we've done that maybe 7 years ago and more. The last paper was like maybe 4 years ago, and you can find it on my GitHub. And there hasn't been a single cryptographer in the entire world that is able to actually break that paper. So you can. Try to break it yourself. That's what Toda IP said. I'm not here to talk about Toda IP. So Toda IP we know already works.
아직까지
And
아무도
again,
깰 수 없대요.
not a single cryptographer in the entire world was able to break it. It's been 4 years. I haven't made any changes. You can look at my GitHub.
4년 전부터.
And I'm not here to talk about Toda IP. I'm here to
침략하지
talk
못했다. 그죠?
about using Toda IP with HyperCycle. Okay, so HyperCycle, effectively, I was called into running HyperCycle by some of the most esteemed AI developers in the world because they are crazy visionaries, and I love crazies because they have some vision that they want the world to do, but maybe they're lacking something. They don't necessarily have everything. Like so a lot of people, for example, criticize somebody with the name Ben Gortzel that is like, oh, he's like super crazy, but not. I love the guy. I think he's got some great visions, and I want to complete him as opposed to just criticize the stuff that he's working on. So a lot of people just criticize, they're like, oh, it will not work. Oh, it will not work. Well, maybe we need to find what's missing and see if it actually can work. The reason why SingularityNet doesn't exist on every single device for peer-to-peer is not SingularityNet's fault. All the work that they've done is great. It's actually Ethereum's fault, first. The second problem is Cardano's fault. And anybody who knows proper computer science would look deeply and would find that that is the problem. Nothing wrong with Ethereum, but it's not.
에코시스템 있잖아요. 거기 아이들이 전부 다 뭐 이렇게 해서 다 문제가 있으면은 이더리움이 원래 잘못됐거나 그렇다는 거죠.
Ethereum itself is probably good for some things, but it's not good for having peer-to-peer for global brain. So that's effectively what Singularity is trying to build. So about a year and 6 months ago, we were in a hackathon in Wyoming, and at the time, Ben Gortzel asked me, he said, it's time to build the Singularity on Toda IP. Did you want to be involved? And I'm like, I don't want to run it. This is teasing me, like my entire life of cybersecurity, cryptography, and AI. You're telling me to put them all in one. This is great. He's like, give me a date. I'm like, October 2022, and precisely October 2022 is when we open the store of HyperCycle. So what's a HyperCycle? So you have two devices that they want to talk to each other.
지금부터 이제 하이퍼사이클 얘기하는 겁니다.
And why is that? Like if somebody doesn't know the necessity or the problem in AI, they can actually look at some of the researchers and the true godfathers of AI that are actually currently dead, like Marvin Minsky. He talked about this in 1983. And in 1986, he published a book on that. It's called Society of Mind. And effectively, when you have many different agents, each and every agent can become like a human. We cooperate, and that's why we govern this planet. But each and every AI agent in the world, they don't necessarily cooperate. They don't. You have inside the Microsoft cluster, they cooperate. Inside the Tencent cluster, they cooperate. Inside of the Google cluster, they cooperate. But if they want them to cooperate together, they cannot. If somebody is building in their basement, in Seoul, some sort of super duper AI agent, nobody finds out about it. They need to wait until they go through some sort of like academic research and all of the stuff to then maybe somebody in Microsoft will adopt it into the Microsoft cluster. But imagine this is the AI that you want to talk to that AI. If they want to talk to each other today, like I showed on a previous screen, there's only two ways to do this. Either central bank or ledger. There is no third way that they can talk to each other. There is a central entity that needs to exist in order to transmit the value.
인간은 여기 있어 아프고 이거 아프고 뭐 이렇게 하면 다 그죠. 내가 이게 좀 통합을 해서 융합을 해서 내가 판단을 내는데 이놈의 기계하고 저 기계하고 융합하는데 두 가지 방법이 있는데 하나는 은행을 통해서 돈으로 받고 하나는 또 레저로 한다.
So this is super exciting. Want to build it on Toda IP. I'm like, I want to run it, and then we call it HyperCycle. So effectively, when you have those agents being able to talk to each other, why would they want to talk to each other? This one is doing some work for this one. And imagine this guy can tell this guy, can you help me solve some problem? But there's like 50 million globally of this, and each and every one they could talk to each other. Let's say you receive a response within 100 milliseconds or 200 milliseconds, and it's fully computed response. Then you might ask the question, how many devices can this talk to in the same time? Maybe 1,000? It's not a million, but maybe 1,000. But if this guy can talk to 1,000 devices at the same time, let's be more conservative. Can we give it 100? If it can't talk to 100 at the same time and it takes 200 milliseconds, you ask the question, can this guy talk to 100? And if it can't talk to 100, okay, then let's take one of those. Can they talk to 100? And then you have like the actual scale.
그러니까 이게 없어지고 그죠? 얘하고 연결하면서 100명을 연결하면은 얘가 또 100명을 또 연결하고 얘가 또 100명 이렇게 해서 연결이 된다는 소리.
In 1 second, basically, you can have 100 to the power 5 if it's one. Okay. So what's 100 to the power 5? Let's do that. Like 100 multiplied by 100 is 10,000. Multiplied by another 100 is 1 million, right? And then multiplied by 100 is 100 million. Multiplied by another 100
is connected by Toda IP.
Network.
The communication between the devices, it uses Toda IP. Otherwise, it won't be able to have finality in that 200 milliseconds.
Toda IP를 이용해서
So
연결하고.
So just effectively, when you have one device is able to connect to 100 devices and get to that finality, and then the other one to get to 100 and so on and so forth, then in 1 second, just if we did the math like here together, we're able to get to 100 million multiplied by 100 is what? 1 billion, 10 billion. So you have one device can actually get work done from like 10 billion devices.
그러니까 연결해서 사용하지 않는 이런 거를 전부 연결해서 우리가 가지고 있는 컴퓨터들이 연결이 되어서 네트워크로 연결이 되어서 토다 IP를 이용해서 사실 은행에 가서 돈 바꾸고 레저 없이도 된다.
Now, how do they talk to each other? When this guy sends instructions to this guy to do work, it sends it as three sets of elements. One element is we call it the SATO server.
아,
And that's
사토시, 사토
basically
서버.
the cryptographic proof. And then you send the data, and then you send the actual instructions. You see those? When the VM, this data is received by the HyperCycleii computation node, the first thing that it received it is the VM. So the VM takes that
Virtual
and
machine.
it checks with the TM first. See, but it takes that because it checks the SAT server is it actually real or not. The TM it comes back to the VM, says like, okay, it's real. This money is real. Then it takes the two other sets of data, the instructions, along with the data, and it sends it to the AI machine. And then the AI machine computes and sends the output to the virtual machine. The virtual machine takes that and then sends it out to whoever requested that. So this is what we're saying that takes, let's say, a couple hundred milliseconds. Once the output is sent, the requester, if you were to talk about this requester, is happy, and the receiver of that work is happy because they got paid. And there you go, look at that. It's like a penny, coin, whatever it is, and you can choose whatever currency you want. You can use won, US dollars, whatnot. Now, of course, you need to imagine this at like a very hyper scale of how you can get.
그래서 모든 이거 노트북 하나 가지고 있으면 돈 번다 그랬어 이 사람이. 이렇게 돈을 버는구나.
So that is HyperCycle이, and yes, it uses the IP behind the scenes. Otherwise, it wouldn't work. And super excited to be here and happy to work with folks that they would want to.
그래서 나중에는 이렇게 연결해가지고
learn more about-
연결시키는 사람이 엄청나게 돈을 번대 17배로 돈을 번대 일반 월급보다. 그래서 이게 뭔가 했더니 이렇게 연결시켜서 여기 돈 받고 여기 돈 받고 이렇게 다 돈을 받는 거구만.
근데 이거 노트북 드리고 조금 가셔야 될 것 같아요.
오케이.
저는 아닌데.
예, he's got to go.
Okay.
오케이.
그래서
오케이. 예.
Oh, perfect. Okay, I'll give you this.
감사합니다.